So this is an example of tension with one of the objects on an incline, right? So blocks of granite are to be hauled up a 15 degrees slope out of a quarry, and dirt is to be dumped into the quarry to fill up old holes. To simplify the process, to design a system in which a granite block on a cart with steel wheels is pulled uphill on steel rails with a dirt-filled bucket that descends vertically into the quarry. So the two objects are connected using a cable. Okay, so we are assuming that the system is frictionless because it says here that we need to ignore friction in the pulley and wheels and ignore the weight of the cable. Okay, so how must the weight of the cart and the weight of the bucket be related in order for the system to move constant or at constant speed? Okay, so meaning acceleration no, is zero. So the first approach is drawing two free body diagrams, one for the bucket and one for the cart. Okay, and take note that the acceleration of the system is zero. So the acceleration of the bucket is zero and acceleration of the cart is zero, but it is or they are moving. Okay, so they are not at rest. So drawing the free body diagram of, let's start with the bucket. Free body diagram of, so may increase the thickness. Okay, so of course we have the gravitational force. Okay, so gravity pulling on the bucket. So its magnitude no, is the weight of the bucket. So let that be W sub B. And since the bucket is connected to the cable, okay, so there is a tension directed upward. And there are no other forces, so only tension and weight of the bucket. So the tension basically on the cable is what is pulling no, the cart up the rail. Okay, so we have here, okay, it's moving no, vertically, so along the y-axis, moving vertically, but with constant speed, so acceleration along the y-axis no, is zero. So therefore, the summation of forces along the y-axis is zero. So we have tension minus the weight of the bucket equals zero, or tension is equal to the weight of the bucket. So the weight of the bucket basically is the one pulling the cart up the rail. Okay, so that of course uh, the bucket will be going down into the quarry. So we have to make an equation relating the weight of the bucket and the weight of the cart. So these two are unknown quantities. So let's label this as equation 1, and we need another equation containing the weight of the cart. So we need the free body diagram no, of the cart. Take note that the cart is moving up the rail. Okay, so its acceleration must be directed no that way. Okay, and it's not um away no from what they call this, the surface no bale of the rail. Okay, so along the axis where the cart moves, so that is where we can find no the acceleration. Okay, so for the free body diagram, so of course we start with the weight. It's always directed no downward, and then since the cart is connected to the cable, so there is a tension towards this direction in the first quadrant. Okay, so this is the same tension with the free body diagram of the bucket because we are assuming that the system is frictionless. So the tension is uniform na throughout the system. Okay, so take note that, okay, this is very important, no? So take note that the um motion is going up, no, the ramp. So the acceleration must be going there. Okay, the bali the motion no, is going there. Okay, and the acceleration. Okay, generally, okay, even if the system is not at equilibrium, no, there is a net force. Okay, so we have the direction of the acceleration going that way. But for this one, okay, it's basically zero, no? So later, no, we'll be writing no, the equations. So the position no, of the acceleration arrow is very important. So it should be parallel no, to the surface of the rail. Okay. So, and also parallel no, to the tension. Okay. Parallel to the length of the cable. Okay. So, if we have this as the direction, this arrow said the direction for the acceleration. Okay. So, we must make the equations from this orientation. No? So, we can have, okay, later for the second law of motion equation, no net for equals mass times acceleration. So we can make that net force be equal to zero. Okay, along this axis, no, although it's inclined at a 15 no degree angle. So syempre, no, so follow na the net force along this basically an axis, no, is zero. Okay, so shouldn't be along the y-axis. Okay, so there is an acceleration no along the y-axis because it's the weight here. There's a gravitational force. Okay, so what we need is we need to have the acceleration along this axis be equal to zero. Okay, and aside from the tension, no, along this axis that is parallel to the surface of the rail, okay, we have one of the components of the weight. Yes, explained in another word problem. Okay, if you haven't seen that problem yet on friction and motion of an object, so the components were introduced there. Okay, so along this axis, you have a component that you can label as W sub x, okay, or weight of the cart, and then specifically, okay, the x component. Okay, if we are going to label this axis as the new x-axis, okay, we can rotate no the axis so that we can make no an equation that is more simple. Okay, and that's explained there. No, the x component of the weight of the cart in terms of the angle theta. Okay, by the way, the angle theta is here. It's 15 degrees. Okay, it's W, no? W of the cart, weight of the cart times sine, okay, of the angle, so sine of 15 degrees. Okay, while here on this axis, no, perpendicular to that component of the weight is the other component of the weight, which is the y component. Or it's the component perpendicular not to the surface of the rail or surface of the incline in general. So this is the y component. So we use the cosine component of the angle. Okay, take note that that 15 degrees is the same 15 degrees here. That's why we use sine component for the x component of the weight, no, because the angle is measured na from the vertical bali, quote unquote vertical, no, if we are rotating na the axis, or the axis perpendicular to the surface of the incline. Okay, and the new x-axis is a axis parallel, okay, to the surface of the incline, because there are other teachers who are using or not using x and y no components if it's already in this topic no nga inclined plane na. So some are using parallel and perpendicular components. Okay, so para we are not going away from the other discussions no para similar to the horizontal surfaces. So we can always no kaning label them as the new set of x and y axis. Okay, having x as the axis parallel no to the surface of the incline and the y-axis being perpendicular to the surface of the incline. Muna siya nailis na ang cosine and sine no, for the components. Okay, so please take note of that. So, okay, it would be best, no, and it's the correct, what they call this, kaning equation, no, if we are going to follow the direction of the motion. Or if you're not sure if it goes up the rail or down the rail or down the incline, okay, so you can make assumptions na maybe it's going down, okay, or moving up. Basta it's along no the surface of the incline, okay, and not along this axis where the weight of the object is located. No, because ang lihok sa object, okay, is dili man paubos, although there's a component no of the weight, and it's not the component the I no, it's actually the entire weight, okay, but naka-affect sa motion is just a portion no of this weight. So since this is moving along no the rail, so ang nakapalihok niya, okay, is only a part of the weight, okay, of the object. And it's this component parallel, okay, to the surface of the rail, no, or the incline. So the acceleration no, along this quote unquote x-axis, okay, is zero. The new axis, no, x-axis is zero. So following the second law of motion, so net force is zero. Okay. So we have tension, no, minus the x component of the weight of the cart. So it's you can write it na lang diretso as W sub C times sine of 15 degrees equals zero. So the tension basically A is equal to this value. Okay, so this is the same tension with the tension in equation 1. So we can label this as equation 2. Okay, then we can equate no the tensions because they are the same. Okay, same cable. So assuming that the pulley is frictionless and we are ignoring the weight no, of the cable. So we have W sub B is equal to W sub C times sine of 15 degrees. Or if we get the approximate value of sine of 15 degrees, so that would be, okay, so 0.2588. So 0.2588 times no the weight of the cart. So therefore the weight of the bucket must be, in terms of percentage, 25.88 approximately, no? Percent, okay, of the weight of cart. Okay, it's lighter than the bucket, so that's actually fine, because the entire system is frictionless. Okay, and with the angle pa yun, okay, so the tension there is suitable, no? At that relationship of the mass, the tension there is suitable for that angle. Okay, so it's how you design, no, the system. Okay, you can also have a non-zero acceleration. It's the same thing. You just equate the net force to mass times whatever is the acceleration of the system. Okay, so can it's a combination of the masses and the acceleration for inclined planes. Okay, if there is friction involved, then we need to consider, no, the normal force. Okay, so along na the perpendicular axis, no, axis perpendicular to the surface of the incline. All right, so that's how you do um a problem using two different, no, free body diagrams. So basically, okay, you can summarize, no, the computations by looking at the entire system. Okay, so we can do a systemic approach. No, so since the two are just connected using a massless cable. Okay, so if you will analyze it, so the bucket, the weight, no, of the bucket simply makes the cart move up, no, the rail. Okay, so although there's a force here resisting, no, that motion, so the combination of the angle, okay, plus the design of the no, the steel wheels and the rail, okay, will help, no, in um, making the cart move up the incline, and then of course on the bucket down the quarry. Okay, so they have the same acceleration. It's a frictionless system, so we can make, okay, a relationship, no, directly, no, between the weight of the bucket and the weight of the cart. Okay, so overall, no, systemic approach. Let me increase the percentage of the display. So using systemic approach, so you look at the entire system. So a system may be composed of two or more objects, no, as long as they are of the same acceleration. Okay, so systemic approach. So for this end, okay, the bucket end, okay, so on the entire system on this end, okay, or this part of the entire system. So it's the weight of the bucket, no, that is present, and it's balanced by the component of the weight of the, what you call this, the cart. Okay, and that component is along the third quadrant. No, so we are combining the two free body diagrams actually. Okay, so let this be the weight of the cart x component. Okay, or the W sub c sine of 15, no, degrees. Okay, so these are the forces, no. So basically, okay, ang ni pull sa imuhang sa tawag ani, na pull sa imuhang cart is the weight of the bucket. Okay. So using the systemic approach, so these two no are equal in magnitude. Okay, so this is not a free body diagram, huh? Just showing lang the directions of what do you call this? Showing lang the directions of the forces. Okay, the gravitational forces or the weights of the two objects. Okay, so again, if you look at the entire system, no, so the weight of the bucket is pulling the cart along no, the rail, okay, and it's equal to that component of the weight of the cart. So it's equal to W sub C times sine of 15 degrees. It's basically the same thing. No? So, pag-analyze lang sa system. So, again, you are combining na the two free body diagrams. Okay, so to have the relationship, okay, between the weight of the bucket and the weight of the cart. So, hope that's clear already. No, so for tension and motion of an object on an incline.